Hi everyone, welcome to class 3. I'm going to start out this class by actually going back to the example that we started last class because we didn't get time to finish it. So I think I'm just going to go ahead and start over to make sure that full problem is all together. So let's look at that one. So last class we were talking about finding the solution to a differential equation by using the Laplace and then inverse Laplace transform. So let's start out by looking at a picture of our system. So we were looking at a mass spring damper system. So we have a spring, we have a damper, we have a simple mass, and then we have an external force. Okay, so we said we're going to look at the position of this mass, x. So it's a spring constant k and a damping coefficient c. Okay, and now we could do our sum of forces on this equation. So on this system, we could say the sum of forces on this mass m. Sorry, let's turn that into a free body diagram instead of just a diagram. We've got some kx and some cx dot. There we go. That's our free body diagram. So we could say our sum of forces equals mass times the acceleration. And so our sum of forces here is F minus kx minus cx dot equals mx double dot. All right. And now let's assume some parameters here. So let's assume, we'll say that mass equals 1 kilogram, C is 4, what would that be, Newton per meter per second, something like that. K equals 3 Newton per meter. F, we'll say, is some step function times 9. So instead of going up to 1 at t equals 0, it's going to go up to 9 at t equals 0. Okay, and then we'll also assume some initial conditions, that the position at time 0 is 1 meter, and the velocity at time 0 is 0. Okay. So now we can take the Laplace transform of our differential equation after we plug in our parameters. So let's go ahead and plug in our parameters and see what that looks like. So we'll have x double dot equals minus 4x dot minus 3x plus 9 times our step function. Okay, now we can take our Laplace transform. And get the Laplace transform of x double dot is equal to the Laplace transform of everything on the right-hand side. Okay, and you can use your tables to do this. So if we look at our tables for the Laplace transform of a second derivative, we should get s squared big X of s minus x times our initial condition x of 0 minus x dot of 0. Okay, and this is equal to the Laplace transform of everything on the right. And so again, you can use your table, find the Laplace transform of x dot. We should just get minus 4 big X of s plus, I believe, oh, sorry, yep. Let's do it this way. Minus 4 times the Laplace transform of x dot, which is s big X of s minus x of 0. Okay, so that was the Laplace transform just of that term. And then we have minus 3 big X, and then plus 9 times the Laplace transform of a step function, which is 1 over s, so that we get 9 over s over here. Okay, so now what I'm going to do is rearrange so that I have all of my big x's on one side of the equation and everything else in terms of s on the right-hand side. Okay, so let's see how that might work. Let's put all of our big s's. Oh, let's fill in our initial conditions too. So x of 0 we said was 1. So we should get s squared big X minus s. X dot of 0 is 0, so that goes away. Minus 4s big X. X of 0 was 1, so we end up with a plus 4 here. Minus 3 big X plus 9 over s. Okay, so all I did was just plug in my initial conditions here, here, and here, and then just rearranged it a little bit. And now let's rearrange some more. All right, so s squared big X. I'm going to bring this to the left-hand side, plus 4sx. Bring this to the left-hand side, plus 3x equals, I'll bring this to the right-hand side, s plus 4 plus 9 over s. All right, now on the left, I'll factor out that big X. So we should have s squared plus 4s plus 3 times big X equals s plus 4 plus 9 over s. And in fact, let's try to get rid of this weird fraction-y thing. We'll multiply both sides by an s. All right, so that should give us s squared plus 4s plus 3 big X equals s squared plus 4s plus 9. All right, and now all I need to do to get my x all on its own is to divide everything by this coefficient on the left. So we should have big X of s is equal to s squared plus 4s plus 9 over s times s squared plus 4s plus 3. Okay, so now we have our Laplace transform of x in terms of a polynomial of s over a polynomial of s. And the next question is, this doesn't appear on my Laplace transform table anywhere. So the next question you might have is, how do we take the inverse Laplace transform of this? And so last class I went through what I called a potentially useful aside, where we talked about how to do partial fraction decomposition. So I'm not going to recover that. So if you need to see partial fraction decomposition reintroduced, go back to the previous lecture and watch that. But for right now, I am just going to use partial fraction decomposition, assuming that you've already seen it before. Okay, so let's actually look a little bit closer at this term. We can factor this further. And we can get it into looking like an s plus 3, s plus 1. That is how you would factor that. All right, so that means that x now equals s squared plus 4s plus 9 over s plus 3, s plus 1. Okay, now partial fraction decomposition allows us to say, all right, I have this thing that looks like this, but I would prefer it to look like something where I've got something on the top over s plus something else on the top over s plus 3 plus something else on the top over s plus 1. All right. And I want the two sides of this equation to be equal. So what I'm going to do on the right-hand side is multiply by each of these terms by a fancy version of 1. All right, so for this first term, I'm going to multiply by something where I take the denominators of all the other terms and multiply by that on top and bottom. So let's see what that looks like. We're going to multiply by s plus 3, s plus 1 over s plus 3, s plus 1 times a over s. All right, so we check with yourself to make sure you agree that this is a very fancy or ugly version of the number 1. We have same stuff on the top and same stuff on the bottom. And we're going to do the same thing for b, multiply the other terms. So we have an s and an s plus 1, s plus 1, s plus 1 times b over s plus 3. Same thing with c. What's left is s and s plus 3. Okay. Now we need to expand what's in the numerator here. So you might already be able to tell that all of these denominators now look like the same denominator that's on the left-hand side. So that's a really good sign. In the denominator of all 3 of these terms, we have an s plus 3, and an s plus 1. It's exactly what we want to happen. Okay, so now I'm going to expand the numerators and set them equal to the numerator on the left-hand side. So if these 2 sides of the equation are going to be equal, the numerators have to be equal and the denominators have to be equal. So what that means is I should have s squared plus 4s plus 9 is equal to whatever this s plus 3s plus 1 times a is. So I FOIL by using squares, so s3, s1. This multiplies to s squared, 3s, 1s, 3. Okay, so we should have a s squared plus a 4s plus 3a, or a3, either one. All right, that's the numerator caused by the first term. Let's do the numerator on the second term. So this one's easier. It's just s squared plus s all times b. So bs squared plus bs. The third term is going to be s squared plus 3s. So cs squared plus c 3s. Okay, now to figure out this a, b, and c, we need to recognize that in order for the left-hand side to be equal to the right-hand side, then the coefficient of s squared on the left has to be equal to the coefficient of s squared on the right. The coefficient of s on the left has to be equal to the coefficient of s on the right, and the coefficient the final constant on the left has to be equal to the final constant on the right. So I'm going to group these terms by the power of s on the right. So I'm just going to rearrange. So let's say 4s plus 9 is equal to a bunch of stuff times s squared plus a bunch of stuff times s plus some extra constant stuff. All right, so let's see if we can fill this in. We've got an a times s squared, that's that one. And we've got a b times s squared, that's that one. And we have a c times s squared, that's that one. All right, that's all my s squared terms. Now let's look at s's. I've got a 4a times s. I've got a b times s. And I've got a 3c times s. That's all the s terms. And then my constant is just 3a. Okay, so this induces 3 equations for us. I need everything in this to be equal to the coefficient times s squared, so that is just 1. So 1 equals a plus b plus c. I need everything over here to be equal to the coefficient of s, so that's 4. So 4 equals 4a plus b plus 3c. And then lastly, I need this constant to equal this. Okay, so we have 9 equals 3a. So now I have 3 different equations and I have 3 different unknowns, a, b, and c. So now I can solve this system of equations for each of these coefficients a, b, and c. So if we divide by 3 here, we can say that a is equal to 3. That means if I plug that in maybe in the first equation, I should get minus 2 equals b plus c. Let's maybe solve for b here. So minus 2 minus c equals b, and we can plug that in the middle equation. So we'll get 4 equals 12, because I plugged in a equals 3. Minus 2 minus c plus 3c. All right, so then we get 2c, 10 equals 4. Should get minus 6 equals 2c, so c equals minus 3. And then we'll plug in we'll plug in c over here on the left. So minus 2 plus 3 equals b, so we should get b equals to 1. All right, so a equals 3, b equals 1, c equals negative 3. All right, so let's now plug that in up here so that our x is now in this form that we really want it to look like. So we'll say big X of s is equal to 3 was a, so that's 3 over s, plus b was 1, so 1 over s plus 3, and c is negative 3, so minus 3 over s plus 1. All right, great. And this is beautiful because these terms do appear, at least down to multiplication by a constant. Those terms do appear on our Laplace transform tables. So now if I wanted to take the inverse Laplace transform of big X of s, I would get 3 times u of t, because the Laplace transform of u of t is 1 over s. And then we would get plus e to the minus 3t u of t, which is the inverse Laplace transform of this term here. And then finally, I have minus 3 times e to the minus t u of t for this last term here. All right. Whoops, this is an inverse Laplace transform. So my final x of t is equal to, at least for all time steps going forward in time from 0, we have 3 plus e to the minus 3t minus 3e to the minus t, all times u of t. So this is a nice way to solve a differential equation with a specific forcing function. Why do I say a specific forcing function? Well, you'll notice back up in our assumptions here, we assumed a specific form. We said we're going to apply a force of 9 times the unit step. Okay? So we assumed a specific forcing function. Now let's look to see what would happen if we had not applied a specific forcing function. What if we took this same differential equation here, we'll copy that, and what if I had left it generic? Instead of saying that f is equal to 9 times u, let's say, what if we had not assumed a specific f of t, and we had assumed all 0 initial conditions? if we had left this generic, and we had assumed x of 0 equals 0 and x dot of 0 equals 0, we could still take the Laplace transform but instead of a specific value of s, we would end up with just some big F of s representing that whatever f is as a function of time, this big F of s is just the Laplace transform of that function. I don't know what that function is, but we'll just call it big F of s for right now. And then I would get minus, let's actually plug in these parameters here. So k we said was 3, c we said was 4, m was 1, so something like this. So I'd have minus 3 big X minus 4 s big X equals s squared big X. So keep in mind this time, we are assuming 0 initial conditions, okay? So I don't have any of those x of zeros and x dots of 0. All right, so now let's solve for output over input. The output of this system is the position that it takes over time. So the output is the value is this x function, and the input is the force that we apply to it. So the input is big F. So let's try to rearrange this equation to find x over f. So we'll try to get all the x's on one side and all the f's on the other. So f of s equals s squared big X plus 3 big X plus 4s x. I'll factor out an x. F of s equals s squared plus 4s plus 3 big X. And I'll need to divide by this and divide by f. So I should have 1 over s squared plus 4s plus 3 equals x over f. And this value is what we call the transfer function. The transfer function. And in fact, if we were going to write our system in block diagram form, we would take that transfer function and we would plug it in to our plant or system block. So our input here is f, our output here is big X of s, and our transfer function g goes in this block here. 1 over s squared plus 4s plus 3. All right. So that, friends, is how we solve for the transfer function of a system. All right. So let's add a little bit more detail about transfer functions and block diagrams. So we just said that a transfer function, let's give us a title here, transfer function we said these are output over input. Output over input. Sometimes we say that this transfer function is g. Our output is usually s and our input is usually r, where c represents the control variable, and r represents the reference, or the input, however you want to call it. Okay, c of s and R of S are polynomials if this is an LTI system. So remember, LTI is linear time invariant. And in fact, we have a property that I want you to know about transfer functions. We say that a transfer function is considered to be, quote, proper if the polynomial of the denominator has a greater let's call it degree than the degree of the denominator or of the numerator. So for example, if we have a transfer function that looks like this, versus a transfer function that looks like this, which one of these is proper? Well, this one on the left, x has a greater exponent in the polynomial on the numerator, which is the opposite of what we want. We want the greater exponent to be in the denominator. Okay, so this one is what we would call proper. And this one would be not proper on the left. Okay, let's look a little bit more at block diagrams. We've seen kind of two very simple block diagrams before. Together we've seen an open loop block diagram where we have just an R of S or a reference comes into a system block and gives our output control signal C of S, and we've got some transfer function in the middle, and we call this open loop. We've also seen a closed loop block diagram. We have our reference signal comes into our system block, gives our output C of S, which is then fed back in. And actually I need to improve this a little bit. This is a summing junction like this, and we call this closed loop. Now these are the two very, very simple versions of these block diagrams. Let's look at slightly more complex block diagrams. In fact, I need to go grab us a picture. Let's grab here. I will copy and paste. We could also see block diagrams that look like this. What you'll notice here is that there are some additional features. So one is that before hitting the controller, we could see what's called an input transducer. Input transducer here. Okay, so this is just another block that's going to take your input or reference and produce a different type of signal before it goes into the controller. So for instance, let's say we're talking about a thermostat. Your input could be the button push by the user on the thermostat box. The input transducer is what translates that physical button push into a control signal. So this might be a voltage proportional to maybe desired temp. Your controller is what takes that desired temp and translates it into some action on the plant. The plant, remember, is your representation of the physics of the system. And then what's also new about this is these disturbances. So we will talk sometimes about rejecting disturbances. So disturbances are things that we didn't add as a control input, but maybe they are things that are maybe a little bit strange about the system. So let's think about, again, our thermostat. We might have something that within the plant, we have something that represents like the maybe the airflow through our house, but we don't account for whether or not the door is open on our house. So maybe it's the middle of hot Florida summer, and this disturbance could be the fact that someone opens the door to the house and lets in a bunch of hot air. And so this disturbs our plant by adding extra heat that we didn't account for within the system block. All right. And we can have disturbances both before and after the plant. It all depends on the type of signal that represents your disturbance. So, for example, if this plant block is a mass spring damper system, the disturbance before the mass spring damper system is like the input to our mass spring damper, which is usually forces. So if we have a disturbance force, that would come in before the plant. If the output of our plant is, let's say, the position of our block, we could have a disturbance outside of the plant if the disturbance was in the form of some like extra position X, right? So it all depends on what type of signal the disturbance is. Okay. Very similarly, we can have disturbances in our closed loop system. We have an input transducer, but then we can also have an output transducer. And this output transducer takes, it's usually in the form of a sensor. So this sensor, for instance, might take as input the actual temp of our room and output a voltage that is proportional to the actual temp, such that when you go into this summing block, you take the desired temperature, or the voltage that is proportional to the desired temp, you subtract, that's why it has the minus here, you subtract the voltage proportional to the actual temp, and what this signal here going into the controller is the error between the two. So this is how much difference you need to make up to go from where the value you're currently at to the value you actually want. Okay, so these are a little bit more complicated block diagrams. Just a couple more comments I want to make before we jump into state space systems. All right. So far we have mostly talked about SISO systems. So SISO is single input, single output, and these are great for transfer function representation. SISO systems are great for transfer functions. My question is, can you do a MIMO system with transfer functions? Sorry, let's write that more clearly. MIMO system. with a transfer function? Sure, turns out yes. Yes, you can. Let's see what that looks like. First, let's look at 2 input, 1 output. Let's see what that block diagram would look like. So let's say I have 2 inputs. I have an R1 of S and I have an R2 of S. We could say that my system, which is made up of subsystems, is actually the sum of R1 times some transfer function G1, R2 times some transfer function G2, and our output is just the sum of these 2 outputs. We just sum them together and give our output, single output C of S. Okay, that was easy enough. Let's look at 2 input, 2 output. This one gets a little more gross. So 2 input, 2 output means that my first input can potentially affect both my first output and my second output. And similarly, my second output can influence both my second input can influence both my first and second output. So let's try to draw that block diagram. I have R1 of S comes in, maybe to some transfer function G1, 1. And that has some effect on output 1, C1 of S. Okay, but it also has some effect on C2. So let's take a copy of R1 and we'll bring it down this way. In fact, there's going to be a signal over here at some point that we're going to have to hop over. And we'll say this is G21. And this gets some influence over C2 of S. It still didn't go the way I wanted. There. Okay, so R1 of S has some influence over C1 and some influence over C2. And now R2 also can affect both. So we'll say R2 goes into some transfer function G1, 2. And that goes into our first output, C1, and these 2 things are added. And just like we did before, we're going to take a copy here of R2. This goes into our final transfer function, G2, 2. And that's going to sum to affect C2. Oof, that got messy. That's a pretty nasty block diagram. And it's only 2 input, 2 output. Can you imagine if we had like 60 inputs and 60 outputs? That would get really intractable really, really quickly. There is a slightly more compact way we could write this. So in other words, we could say that C1 of S is equal to R1 times G11 plus R2 times G12. C2 of S is equal to R1 G21 plus R2 G22. And we can write this more neatly in linear algebra form. In fact, we could say that the vector of our control signals is equal to a matrix of transfer functions times a vector of our reference signals. Okay, so this here is a matrix of transfer functions. But this is still pretty messy. Using transfer functions and block diagrams for MIMO systems gets really messy really fast. So in all reality, in all practical applications, instead of using transfer functions, we usually use state space representation for MIMO systems. So let's talk a lot more about state space representation. So state space representation is a time domain modern approach, also known as a time domain more modern approach. And I say modern because usually we refer to transfer functions as being classical controls. All right, and this state space representation is easier for handling MIMO systems. Multi-input, multi-output systems. But the representation can be a little less intuitive. And we're going to need to talk about this idea of a state of a system. Okay, and we're going to do that through a couple of definitions and then some examples. So, first definition is the idea of system variables. System variables. Okay, system variables are any variable that may change with time in response to an input or an initial condition. Okay, so if we think about a mass spring damper system, if we take it and we pull it away from its resting location, so we give it some non-zero initial condition and we let it go, what are the things that can change with time? Well, obviously the position is going to change with time because it's going to oscillate back and forth. It's going to have some velocity that's changing in time, some acceleration, some jerks, some snap, crackle, pop. You could go on and on and on and on. Okay, so there are lots of variables that describe the motion of this system that change in time. But these state variables are more specific than the system variables. There are lots and lots of system variables, but the state variables are the smallest set of linearly independent system variables such that the values of its members at time t0 with no inputs completely determines all system variables for all time. T greater than or equal to T0. Okay, so that is probably still a little bit vague, and so what I want to do is talk about a specific example. And as almost always, we're going to talk about a block. We mechanical engineers love our blocks. So let's talk about a block sliding. We've got some surface. We've got some mass sitting on this surface. We're going to describe some position. We're going to give it a force. We'll say this is our input. And let's say our differential equation or equation of motion of this system is mx double dot equals f of t minus some viscous friction. So there's some friction between the block and the ground that we're going to model with this viscous friction term. Okay. In order to know where the block is for all time, we need to know, what do we need to know about this system? In order to know where this block is for all time, we need to know what? We need to know the initial position, all right, because we need to know what initial x you're at in order to know what x's you move to over time. And then we need to know an initial velocity. After we know this position and this velocity, everything else is known. So why do we not include acceleration? Well, acceleration here is completely determined by this x dot of t. Every other future derivative of x double dot is just the time derivative of this equation, or the multiple time derivatives of this equation. So once we know an initial position and initial velocity, if our forcing function is none, right? Because we said no inputs. If we assume no inputs, then our position and velocity completely define all other system variables. So we need to know x. We really only need to know x of 0 and x dot of 0. The equation of motion above means that we don't need x double dot as a state variable. Okay, so now let's take this idea of a state and let's talk about state space. State space is the n-dimensional space whose axes are the state variables. So for example, with our sliding block, our state variables were x and x dot. So I want you to think about a space as being like this Cartesian plane of x and x dot. And now let's think about maybe how that state evolves over time. If we take it from some position that is non-zero, let's say we took it from some non-zero position. I'm going to have to redraw. With zero velocity. So we pull our block away from that spring by a little bit. When we let it go with zero, we start out with zero velocity. That's why I'm on this horizontal plane here. When I let it go, it's going to pick up velocity and it's going to return towards the origin. And maybe it oscillates back and forth a little bit, or maybe the viscous friction is enough that viscous friction starts to slow down the block, and eventually it settles back at the origin with zero velocity. Okay, so this is the trajectory that our system follows through the state space because of some non-zero initial condition. All right, now let's look at what the state space equations look like for an LTI system. State space equations, for a linear time invariant system. Now, if you take away one thing from this class, I want it to be the state space form. This is what we're calling the state space form. We call this first equation the state equation. And this second we call the output equation. And together, these two equations form what we call the state space form. Okay, so this reads x dot equals ax plus bu and y equals cx plus du. Keep in mind here that I am showing vectors with this over arrow and matrices as capital letters. Okay, so x and u are both vectors, a, b, c, and d are both matrices. All right, let's define our x vector here. This is the vector made up of state variables, x1, x2, all the way down to xn. We call this our state vector. Similarly, y is our output vector, and it's made of outputs y1, y2, down to yp, and it's known as our output vector. Lastly, u of t is our input vector made up of input 1, input 2, down to input m, known as our input vector. All right, so you'll notice that the length of each of these vectors is defined by this little subscript in the last location. So the state vector is an n row by 1 column vector. Output is a p row by 1 column, and input is a m row by 1 column. Okay. Similarly, we'll define our A, B, C, and D, our matrices. A is always going to be square. It is an n by n system matrix. B is an n by m input matrix. C is p by n output matrix. And D here is our P by M feed forward matrix. Okay, I'll give a little bit of foreshadowing, just a little bit of interesting things here. If all the eigenvalues of A have negative real parts. I say this because eigenvalues can be complex numbers where you have part of the number is an imaginary portion, but if the real parts are all negative, then the system is stable without control input U. Okay, so this is just a foreshadowing. We will cover stability in more detail later. And then we can also determine if this system is controllable based on A and B matrices. All right. And that's probably actually more foreshadowing than we will get into in this class. So controllability and reachability are probably things that we're not going to have time to cover, but you might see in, for instance, a linear systems course. Okay. Now let's go through the process of looking at a dynamical system and determining how to put that system into state space form. So, process for putting a dynamical system into state space form. This is going to be a really important part of this lecture. So you will need to know the process for putting a dynamical system into state space form. So first of all, we still need this system to be LTI. So first we need to check if the system is LTI. So in other words, we need to check that all your inputs and outputs and the derivatives of these are multiplied by constant coefficients. Oops. All right. Once we are certain that our system is LTI, we can then count the state variables. Count the state variables. And we have a very particular process for doing so. So what you'll need to do is find the lowest and highest order derivative of every time varying quantity and then the number of state variables n is equal to the sum of the highest order minus lowest order for each variable. Let's do a quick example to see what that means. So for example, if I have s double dot of t equals s plus f of t. My two variables here are f of t and s of t. Now let's find the highest order and the lowest order for each of these. Okay, the highest order of s of t is going to be the highest number of derivatives on s of t. So in this equation, the highest number of derivatives on s of t is the second derivative, so that is a second order. The lowest order on s of t is 0 derivatives. I just have a plain s of t, so my lowest order is 0. And then for f of t, my highest order is 0. I have no derivatives on f of t, and my lowest derivative is 0 derivatives on f of t. So my n here is equal to the highest order minus the lowest order for f of t, so 0 minus 0, plus the highest minus the lowest for s. So n here is equal to 2. All right, so my state vector has 2 quantities in it for this system. Let's do another example. Let's say I have s triple dot equals s dot plus f dot of t. Let's do that same process again. I have an f varying in time and I have an s varying in time. Highest order, lowest order. All right, highest order of f of t, whoopsies. Highest order of f of t, I have a single derivative. So I have 1. Oh, sorry. This is a system described by 2 equations, not just 1 equation. So this is a system described by 2 equations of motion. There we go. Okay. So now I still have 2 time varying quantities, f and s. So my highest order derivative of f is this first derivative. So highest is 1, lowest is 0 derivatives. Highest order of s is this 3 derivatives on s. Lowest is this 1 derivative on s. So n here equals 1 minus 0 plus 3 minus 1. So this equals 1 plus 2 equals 3. Okay, so that's the number of items in my state vector. So our state vector would be something that looks like something here, something here, something here. 3 quantities. Okay, so now we know the number of states. Now we need to figure out what are the actual states. So we know We know the actual state vector. Okay, so next thing we need to do, we'll put this as direction number 3. Step number 3 is list the state variables in a state vector. To do so, we will take each time varying quantity and fill in the state vector starting with the lowest order derivatives up to the second highest derivative. Do not include the highest order derivative. Let's do an example. So for example, we have s double dot of t equals s of t plus f of t. Let's figure out the number of states. So we have 2 time varying quantities, highest order, lowest order. Highest order of f is 0 derivatives, lowest order of f is 0 derivatives, highest order of s is 2 derivatives, and then lowest is 0 derivatives. So n equals 0 minus 0 plus 2 minus 0, so n equals 2. So I know that my state vector has 2 quantities. Now I need to figure out what those quantities are. So let's start with our s variable, and we will fill in our lowest order derivative up to our second highest order derivative. So my lowest order derivative of s is that 0th order, so I just have s. Then if I go up 1, I have s dot, and I do not include the highest order derivative, so I do not include s double dot. Now, do we need to include any f's in this state? Well, my lowest order f is the 0th order, no derivatives, but my highest order is also 0 derivatives, and I do not include the highest. So there are no f values in this vector, which is great because I've already filled out the 2 quantities that I know I needed. 2 quantities, and these are, of course, in terms of time. State space notation is a time representation, time domain representation. Okay, let's do that again for our other example. Let's go back to that s triple dot equals s dot plus f dot. And f equals s double dot. Okay, I'm just going to leave out my dependencies just for expediency. We already determined that n equals to 3. We determined that in that previous example. We just need to figure out what are the 3 quantities that go in here. So x equals something with 3 quantities. Oops. All right, so let's start with our lowest order of s. Our lowest order of s in these 2 equations is the first derivative. So I need to start with this first quantity as s dot. I go up 1, I get my second order, but I do not include my highest order of s, so I do not include s triple dot. Okay, now let's start with our f terms. My lowest order of f is the 0th derivative, so just f, and then my highest order is that very next one, and we do not include the highest order, so I do not include this f dot, which is good because we already know that we've filled out the 3 items that go into this vector. Excellent. So now we know the state vector for these 2 systems. Step 4 says find x dot and write it in terms of x of t and u of t. So again, let's find example, s double dot equals s plus f. We decided that my state here was equal to s dot. We did that in the previous step. So let's find the time derivative of this. So x dot is just the time derivative of each of these quantities. So this is really just s dot, s double dot. All right, but I want to write this in terms of x and u. So I could say that x dot is equal to, and actually for this system, let's say that this f here is our u. We'll say that this is our control input, is this force. So I can write this x dot is some matrix times my state vector plus some matrix times, whoopsies, my u vector, which is here just f of t. So you'll see I'm putting this into ax plus bu. So x dot equals ax plus bu is the first equation of that state space form. So I need to now figure out what goes into this A matrix and what goes into the B matrix. All right, so let's look at x dot. So basically what I need is this thing on the left-hand side to be equal to s dot, s double dot. That's the definition of x dot. So if I were to multiply this first row of A times this vector x, I need to end up with the value s dot. That is what forms that first row of x dot. So are there any s's in here? No, it's just an s dot. So we'll multiply s times 0. Are there any s dots over here? Well, yeah, that's what's right there. So let's multiply s dot times 1. Now let's look over here. Are there any f's times this value? Are there any f's in this first row of x dot? Well, no. Now let's look at s double dot. We have an equation for what s double dot should be equal to, and that is from our equation of motion. So what we need to do is write this such that the second row of x dot is equal to s plus f. All right. So the f term is going to be determined by multiplying this b times f. So let's ignore it for now. And then let's look over here. Do we need any s's when we multiply this second row of A times this vector x? Yes, there is one s. Are there any s dots in this? No. So we'll multiply s dot times 0. Now we can look at f over here. Are there any f's down here? Yep, there's one f. So we'll multiply that by 1. All right. So doing this manipulation takes a little bit of practice to figure out what needs to multiply what. And in fact, you can go ahead and check yourself. If you go ahead and do the matrix multiplication here and the matrix multiplication here, you want to convince yourself that they result in s dot and then the definition of s double dot, which is s plus f. So we can do that. Let's do a times x. So I have a 0 times s plus 1 times s dot. And then I have a 1 times s plus a 0 times s dot. So that goes away because it multiplies by 0. I have an s dot and then an s. And then over here I have a 0 times f and I have a 1 times f. If I combine these two vectors, I should get s dot and s plus f. Are the left and the right equal? Yes, they are. So that means we wrote our state space form appropriately. Okay, I'm going to leave it there for now. We will practice this process again in the next lecture on state space representation, which comes after our MATLAB workshop. So our very next class, we'll do quiz 1 and a MATLAB workshop, and then the class after that, we will finish up state space representation. All right, thanks for your time. Bye.